On a recent visit with my doctor, we had a long conversation about my family history. In fact, she wanted to know if I had certain illnesses or diseases and if they ran in my family. Well, we started on my mom's side and we went back as far as I could remember, back to my grandmother, even my great-grandmother. Now, several times I didn't know if people had those diseases or not. I was trying to remember from memory. And then, we went through my dad's side of the family, on to my grandparents, and then my great-grandparents. And so just when I thought we were finished, she asked about my siblings. Okay, so I answered as much as I knew about my two brothers. And you would have thought she would have stopped there. Well, you'd be wrong. She asked about my aunts and uncles and cousins. So by now, our time was almost up. And I have to admit, I was pretty frustrated that we didn't get a chance to actually talk about me. But what I did know was that she was creating a profile of my family health history. And then she began to tell me certain illnesses that I might be genetic to, and what I could do to avoid getting them. She used information from the people in my family to create a model for me, a multiple regression, where I was the response and my family members were the predictors. Now, as I think about my health regression equation, the two predictors that I'm probably most related to or most correlated with, they're likely to be highly significant in my model. And that would be my mom and my dad. Now, after them might come my brothers, since we share the same parents. And in fact, there may even be some predictors in my model that aren't significant at all, maybe like my distant cousins. Now, by including all the possible predictors that are related to me, I now have a richer, more accurate model of my health. Now, this is the concept behind multiple linear regression. Let's recall, when we first started examining the relationship between two variables, we used the t-test. Now, these allowed us to determine if there was a statistically significant relationship between two variables. And so we then moved on to simple linear regression, which allowed us to then fit a line to a predictor versus a response. Now, while these are useful in the case where we only have two variables, it's more often that we're going to have to work with data that has multiple predictors. So multiple regression is a statistical tool that's going to let us examine how multiple predictor variables can be used to model a response variable. So what we've done is we've generalized our simple linear regression methodology in order to now describe the relationship between a response variable y and a set of predictors, right? X1, X2, out to Xn in terms of a linear function. So these variables, X1, X2, out to Xn, these are the n-explanatory variables, right? Because they explain what's happening in the response variables. Right? We also call them the predictor variables or the independent variable. Now, the p-value for these explanatory variables, it can be taken to be a rough measure for how helpful that explanatory variable is to the model. And so our multiple linear regression equation is going to give us those p-values. Now, if we have insignificant variables, we can just prune them from our model, as long as it doesn't decrease our adjusted R-squared. All right, here's our multiple linear regression model. Notice now we're regressing y, not just on a slope plus an intercept, but y equals beta naught plus beta 1 xi plus beta 2 xi, all the way out to beta p xp, and plus our epsilon term. Now these beta naught, beta 1 out to beta p, these are the coefficients, the parameters. And your x1, x2 out to xp, these are my explanatory variables. And epsilon, that's a normal 0 sigma squared error term. And so after we collect the data, we've got a collection of observations. And these kind of go in pairs. So imagine that you've got y1, and then for y1, I have all of my p predictors. So x11, x21 out to xp1 are going to be associated with that value. And then at my next observation, y2, I've got my predictors again, x12, x22 out to xp2, and so on. So keep track of our data. It's almost in a matrix form now, right? Because we've got a multiple linear equation. Now, as in the case of simple linear regression, we want to find the equation of the line that best fits the data. So in this case, it's going to mean that we're going to find beta naught, beta 1 out to beta p, all of those hats, such that the fitted values, yi hat, are close as possible to our observed values, y sub I. Let's look at a data set in R and see if we can model it as a multiple linear regression. Here we're going to analyze the diabetes in Pima Indian women. And so this data was collected on a population of women 21 and older of Pima Indian heritage, and they were living near Phoenix, Arizona at the time. Now, the women were tested for diabetes according to the World Health Organization criteria. Now, this is a very rich data set, and it has the following columns. First, we're given the NPreg, which is the number of pregnancies. GLU tells us the plasma glucose concentration in an oral glucose tolerance test. BP gives us the diastolic blood pressure, and skin tells us the tricep skin fold thickness. We're also given the body mass index, or BMI. Also, PED, which is a diabetes pedigree function. This gives us information on relatives that might have diabetes. And then for each woman, we have her age in years and then type. This is yes or no as to whether or not the woman is diabetic according to the World Health Organization criteria. All right, let's load this data set into R. And it actually lives in the mass package. So here's how we'd install that. Do the install.packages command of mass. That's our library. And then library of mass brings it up into our session so that we can work with it. Now data is going to call our data set out. The data is pima.tr, and that's a capital P. Let's look at head of Pima. So that's going to give us the first couple of rows of the data set, just so we can start to see what it looks like. Now here you'll see the columns of our data set, number of pregnancies, glucose, blood pressure, skin, and so on. And you see the associated values. You also see at the bottom there, it tells us that there are 200 of these data points. And now let's look at a summary statistic. So here's summary of our Pima data. Well, a couple of things really stand out here. And in particular, check out some of those maximum values. Notice the number of pregnancies. Minimum of 0, that makes sense. Median of 2, okay, I can go with that. Maximum of 14, wow. That's a lot of babies to come out of one woman. Notice also, here we see age. So our age ranges again from a minimum of 21 to a maximum of 63. That's pretty sensible. Body mass index goes from a minimum of 18.2 up to a maximum of 47.9. Let me draw your attention to PED, which is the diabetes index. Notice it goes from a minimum of 0.08 to a maximum of 2.28. And notice how far away that is from our third quantile of that variable. So that might actually indicate a possible outlier. Another thing I want to highlight is BMI. So you see the range of BMI, but look at the median and the mean, 32.8 and 32.31. When you see a median and a mean so close together, it almost helps to give you a little bit of assurance that that might be an underlying normal population. Because for the normal, we know that our mean is equivalent to the median, which is equal to the mode of the distribution. So anytime you see a mean and median that are that close, you may want to ask yourself about normality. Now, all of these variables are quantitative, except for type. So type is our categorical variable, which is yes if you're diseased and no if our woman is not diseased. Now let's just look at some summary statistics of our data, and in particular, some graphical summary statistics. Here we're going to do a histogram of blood pressure, right? And again, we see that absolutely this is a nice normally distributed data set, beautifully centered and nice tails, not skewed, just a nice histogram of our blood pressure. And we could also do a density plot of that. And notice how the density plot likewise conforms normality. Now, check out a pairs plot of our data. Here are 4 of our data values, the number of pregnancy, glucose, blood pressure, and skin. And there doesn't appear to be a strong relationship in these data values. And in fact, if you look closely at skin, it appears that that point actually is an outlier. There's an outlier in that data that's sort of hanging around. If you look on the x-axis on the bottom or on the y-axis going toward the top, you'll see this point that's separated from the data. So that's an indication that maybe that's a value that we might need to remove. Here's a pairs plot of the other quantitative values, BMI, PED, age, and type. And notice you see there's a slight relationship between body mass index and PED, which is our degree of diabetes. Now we can do a correlation analysis of our data. And this is going to tell us the relationship between our variables. Most of these correlations are at or below 0.34. The highest would be between body mass index and skin, which is our tricep skin fold, at 0.66. And then age and number of pregnancies is correlated at 0.6. So let's fit a multiple linear regression model to body mass index with the rest of our variables as explanatory variables. Here's how we do that in R. We're going to call that just LM1, our first linear model, and it's equal to BMI, or body mass index. We're going to regress it on in preg, GLU, BP, skin, PED, age, and type. And so we're adding all of those variables from our data, which is PIMA. And then the summary of LM1 command is going to give us a summary of that multiple linear model. Notice here's the output that R gives us. So again, you see the model that we called. You also see the residuals. Now, the median looks okay, but if you look at the minimum residual, minus 19, and even the maximum residual, it's starting to get pretty far away from 3 standard deviations from the center. So remember, our assumption about the residuals is normality, and usually standard normal with a mean of 0 and a variance of 1. So we've got some residuals that are further out in the tails that we'd probably like to see. And that might be an indicator that our residuals aren't conforming to normality. So we'd have to do a QQ test on those. Let's look at the coefficients. So here you see the coefficients for each of our model parameters plus the intercept term. So intercept followed by the rest of our x values. And then you see a column of the estimates. These are your beta sub I. So your beta naught, your beta 1, your beta 2, all the way out to your beta p. Next to that, you see the standard error. So R calculates the standard error for each of those coefficient estimates. You see the associated t-value because it's automatically doing a test to see if any one of those coefficients is equal to 0. And then that's the p-value. So your p-value tells you significance. Low p-values are really what you want to look for, right? Things that are really close to 0 or less than 0.05. Anything above about 0.05 or 0.1 tells you that that variable is not significant in the model. So we're not going to be able to use it in our final multiple regression equation. Now, we could go through and think hard about which variables to include. We could also try to automate that process. And that's what stepwise regression does for you. It actually lets us drop insignificant variables one by one. And so this is particularly useful if you have many potential explanatory variables. Now, not all of our x variables are significant. And as I mentioned, we can use stepwise regression on them. But R also has a command called drop one, where we can drop the most insignificant parameter out one at a time. And that also lets us see the output in R. So let's use the drop one command on our data. Right, here's the first output of drop one. Now notice that the result that it gives you is slightly different from the result that you get when you run a regular linear model multiple regression. So in the first column, it has your model. So you see where we modeled BMI on all of our predictors. And then that first column also gives you all of your predictors, followed by their sum of squares. Now the sum of squares is actually one way that we might think to eliminate variables from our model. So you could actually look at the variable that has the smallest sum of squares, in this case would be number of pregnancies, and remove it from the model. But drop one does more than that. It also gives you other criteria that you could use to clean up your regression model. That next column, RSS, is the residual sum of squares. So another way to drop a variable from your model, choose the one that has the smallest residual sum of squares. Next, you see the AIC. We haven't talked about that yet, but it's the Akaki information criteria. Small values of that indicate that that variable should be removed from your model. So that's also a method that you could use. The next column is the F value. So the F value is used to test whether that parameter is significant, probably at the 5% level or at the 1% level. And then your last column is your p-value. You could also use your p-value as a criteria to decide which variable to move. In this case, if you're using your p-value, you'd want to choose the largest p-value, and that would be the variable that you'd remove from your model. So here, where's our largest p-value? Well, it looks like that's that number of pregnancies, which is about 0.87. So let's take that out of our model and see how it updates. And note how our residual sum of squares and our sum of squares is going to shift. All right, here you see where we've removed the number of pregnancies from our model. Notice here, our residual sum of squares has actually shifted a little bit to accommodate the loss of that variable, along with our sum of squares. Now you'll see, if you look at your p-values, we then want to go down that list, if that's our criteria, and choose the next highest p-value, which occurs at glucose. So let's take glucose out of our model using drop one. All right, here's our resulting model. So BP plus skin plus PEG plus age plus type. Notice again, some slight shifting of your sum of squares. So skin has the highest sum of squares. It's clearly the most significant with body mass index. And the rest of them are just sort of fighting over the scraps. Same with your residual sum of squares. Look how skin encompasses 6,454 of the residual sum of squares. And all the others are much less than that. Your AIC for skin is the highest, your F value really high, and look at that super significant P value. So right now you're starting to see what values are going to be significant in our model. Skin's probably going to be one of them. A second runner-up might be type. Notice it already has a significant p-value at the 5% level. But we still have p-values that aren't significant, and the highest one would be BP, or blood pressure. So this would be the next one to take out of your model. Let's do that. All right, here's our next model, we've got body mass index modeled on skin plus peg plus age plus type. Notice here, again, skin is winning with the sum of squares, but it's decreased because we've eliminated a lot of variables out of our model. We've also dropped the level of our sum of squares. The residual sum of squares is still captured by skin. And notice the AIC. So your AIC has shifted. In this case, if we were using the AIC as a criteria to eliminate the next variable, it would be age because age has the lowest AIC. You see our F value and then our associated P values. So based on P value as well, we would get rid of age because the P value is the most insignificant. All right, let's take that out of our model. Nice. Now we're modeling the body mass index as a function of skin plus peg plus type. Notice here, nice sum of squares. Again, skin is giving us the most information for this model, which is represented in the large sum of squares. Likewise for the residuals, it's the largest of the residuals. But notice your p-values. Now you've got all three of your variables significant at the 5% level. So this would actually be the final model for our data. Now, there's nothing that stops you from asking lots of questions from your data. We could also model glucose as a function of the other predictor variables. Here's how we do that in R. Let's call that LM3. And so this is a linear model of glucose as a function of our other parameters. Let's look at a summary of that now. Here we see the residuals. Notice the minimum and maximum residual value. That should automatically stand out that there's probably some heteroscedasticity in your residuals because of the size of those. Here you see the coefficient estimates for this particular model. And notice your p-values. You've got an intercept term that's significant and an age term that's significant. So in this case, we would go through that drop process to get down to exactly which variables would be best at modeling glucose. Don't forget, we need to check the conditions of our model. So we can check for linearity by looking at a residual plot. Here's a residual plot of our data. We've got nice spread in it, centered at 0, and well balanced above and below the line. We can also check for normality and constant variance by looking at a histogram and our QQ plot. So here you see the QQ plot, and it nicely fits along the normal line. Now, the PIMA data set is nice because it has several quantitative predictors, and the predictors aren't highly correlated. But what happens when we have predictors that are correlated? Let's go back to our motor trends car data, and let's fit now a multiple regression model by including more explanatory variables. Here's how we load the MT cars data set. So library data sets and data MT cars. Now we're going to add horsepower to our model. So now our model is going to be y equals beta naught plus beta 1 weight plus beta 2 horsepower plus epsilon, where beta naught is our y-intercept, beta 1 is our regression coefficient for weight, and beta 2 is our regression coefficient for horsepower. Now notice here, here's my miles per gallon underscore model and my linear model fit, right? With miles per gallon now modeled on these two variables. So here we see the associated output. And so the way that we're approaching the MT cars data set is sort of the opposite way as we approach the PIMA data set. With PIMA, we sort of said, hey, let's just add everything and drop one. With MT cars, we're going to see how does our model change as we add variables to it. All right, notice here you have the estimate for weight, minus 3.8 approximately, our estimate for horsepower, minus 0.03, and our estimate for the intercept, 37.2. You see those associated standard errors and p-values, and notice that all three of our parameters are significant at the 5% level. Now, the coefficients for each of our explanatory variables. What does that do? So the coefficient for each explanatory variable tells us the predicted change in y for a 1 unit change in x. right, given that we've held all the other explanatory variables fixed. So for example, as weight increases by 1, the miles per gallon are going to decrease by 3.877. So that's the estimate's coefficient. Likewise, as horsepower increases by 1 unit, miles per gallon will decrease by 0.0317. Now, intuitively, this makes sense, right? The heavier my car gets, the lower miles per gallon I'm going to tend to get. Now, the p-value for each of those coefficients tells us whether it's a significant predictor of y, given that the other explanatory variables are in the model. Now, notice here that the p-values for both weight and horsepower are significant. Now, this model gives us a multiple r-squared value of 0.82 and an adjusted r-squared value of approximately 0.81, meaning 81.48% of the variation in y can be explained by a linear regression model with horsepower and weight. Now, it's hard to imagine improving on this model. Now, if explanatory variables are associated with each other, then their coefficients and their p-values are going to change depending on what else is in the model. Here we see the correlation between weight and horsepower of around 65%. So that's actually getting a little high. Is it possible that these predictors are collinear, meaning that they're highly correlated or they contribute the same information to the model? Well, here's the code. Since we have several predictor variables in our MT-CARS data set, now we're going to put them all in the model, just to see if we can improve on it even more. An easier way to do that is to do miles per gallon underscore model equals LM of MPG tilde and a period, just a period, followed by a comma and data equals MT-CARS. This period says, I want to model miles per gallon on every other variable in the data MT-CARS. So no longer do you have to type out everything. The period automatically tells R that you want to use that entire data set. Now here's the output from our multiple linear regression fit. You see the estimates in the second column, the standard errors, but I want to draw your attention to the p-values. Not one of them is significant. We added every variable to our model, and none of them were significant. Well, why is that? Well, what happens is this. A model that uses all of the variables, well, it sometimes doesn't perform as well as our weight and our horsepower, just based on r-squared. And actually, if you look at the adjusted r-squared, it went down. It was 0.8148 with just weight and horsepower, went down to 0.8066 with all of our variables. So we see that when we add variables that have very little relationship with the response, or even variables that are too correlated or collinear with one another, we actually get a poor result. Now remember, the adjusted r-squared, this is like r-squared, but it's going to take into account the number of explanatory variables that we have. So as the explanatory variables increase, our adjusted r-squared gets smaller than r-squared. It's going to actually penalize us for adding unnecessary predictors to the model. Now, adding more variables will only make your r-squared larger, right? Remember, the more predictors we have in the model, the more we consume those regression sum of squares. And r-squared is just the ratio of your regression sum of squares to the total sum of squares. So it's always going to increase with additional predictor variables. Now, one problem in our data, as you saw, is that our variables are correlated. And you can actually see this when you do a pairs plot. Look at this pairs plot of miles per gallon with DISP and horsepower. Notice all three of these variables are correlated with each other. Likewise here, you see a pairs plot of the variables drat, weight, and Q-set. Now there's less of a relationship between these three, but you still see some clustering. And here's a pairs plot of our entire data set, at least all of the quantitative variables. Notice even at this level, you can see where there's a lot of linear relationship or relationships between those variables. Now, because we have highly correlated variables, this is going to lead us to model misspecification. Check out your correlation matrix for those quantitative variables. And notice that many of them are very high. So miles per gallon and DISP minus 0.85. You see horsepower and DISP at 0.79. Miles per gallon and horsepower is also high. So this is really causing R to get confused about which of these variables is going to be best as a predictor. In fact, it's possible to actually overfit a model by including too many explanatory variables. We have to use the principle of parsimony. The simplest, most efficient model is the best. Because the fewer coefficients that our model has to estimate, the better those coefficients will be estimated. Now we can find the best model by pruning, and we can step through the predictor variables and remove the ones that are not significant. One way we could do that is by choosing the model that has the highest adjusted R squared. Right? Now this assumes that we choose to evaluate the success on our model by the percentage of the variability that the response is explained by explanatory variables. Now, the p-value for an explanatory variable, this can be taken as a rough measure for how helpful that explanatory variable is to our model. If we've got insignificant variables, we just prune them from our model. Let's do a stepwise regression on our linear model fit of miles per gallon with all of our data. Remember, this is going to just automatically spit out the best model to you. And here's the output from our stepwise regression model. The best estimate that it gives us has 3 parameters in addition to our intercept term: weight, Q-set, and AM. Here you see the estimates and the standard errors along with their associated p-values. Now, the summary of doing a successful regression analysis involves multiple steps. We explore our data, fit the model using least squares, use the model to interpret the coefficients and make predictions, check model assumptions, and then do inference. But regression is a family of tools, and least squares is just one of those tools. You could also look for relationships between the explanatory variables. If they're too strongly correlated, perhaps both of them aren't really necessary. And what if one of your assumptions aren't met? Well, this is a pitfall that we commonly run into. Nonlinearity, where we have to transform the data. We'll actually learn about polynomial regression in a future lecture that accommodates that. And what about with your residuals, if they're not constant? Well, we could do something even more than just a transform. We could do a weighted version of our least squares regression. But once you get to your multiple linear regression and it meets all your assumptions, it's all worthwhile. It can improve a library. Multiple regression can improve your health and maybe even save your life.